Hello once more. I would like to announce that for participants who are here at IT for Innovations, we have already the quantum computer presented here, and at 2:30 we are going to look at the device. So I encourage all online participants who might have opportunity to come here for our quantum computer seminars in person to do so from the next seminar. And today's seminars will be about quantum error correction, and our speaker is Richard Kukulski, who obtained his PhD in on Institute of Theoretical and Applied Informatics in Polish Academy of Science in Gliwice. Uh, yeah, I will give you the microphone.
Thank you, Michał, for the introduction. And thank you all for giving me this opportunity to present some seminar about probabilistic quantum error correction. So today I will be talking about error correction, about post-processing, and about how it can be applied to current noisy devices that are available to us, on which we can do quantum experiments. So what we will learn today is we will discuss some basics of quantum error correction. We will discuss noise models. We will discuss then the probabilistic version of quantum error correction, the definition, some results about this. And we will try to apply for given noise models this probabilistic version of quantum error correction to see what we can achieve, what we can gain, what is the threshold. What I will not discuss today, because it would get our discussion one step further, is error mitigation stuff when we are post-processing classical outputs of quantum computing procedures, and fault tolerancy, which allows us to achieve some supremacy. And you can see, if somebody is following up recent papers, that we are at the edge of the threshold theorem from the practical point of view, but still the scalability is a missing factor. So let me give you a quick recap for information processing in quantum information theory. I would like to keep this seminar in mathematical way, that we will be dealing with some equations, with some formal definitions of quantum operations, measurements, and quantum states. So in general, the whole transformation of quantum information in quantum information theory can be seen as a preparing some initial state here. We are starting from some initial state cat 00, and we are getting to some encoded input data that can contain some information about some real variables that we have, and we want to put it in the quantum way. We're dealing with the state, quantum state raw. Then this quantum state raw can be somehow transformed. It can be transformed generally by the object, but the operation, which is called quantum channel, that will take a quantum state and keep it as a quantum state. And this one, we have deterministic description of this evolution. We know the mathematical description in perfect world, what will be the output of such an operation. But what we will see doing measurement is some output, we will call it label, here label I, that it will be some discrete variable. And each of this variable can occur with some probability given by the Born rule. So actually, information processing, you have deterministic stuff and you have probabilistic evolution. That's why this is something which is different from classical computation. There are, of course, many more stuff. We will discuss some of them later. And what is the problem? The problem is we can have a lot of imperfections in our computing. So, for example, our initial state can be prepared not perfectly. Then we may be dealing with some interactions with the environment given by some extended channel that will rotate our state, that will take out some useful information from our quantum state, and it will make our computation noisy. And finally, we can deal with some unwanted interactions from eavesdropper that can harm our algorithm by doing some thoughtful experiments that will, for example, through interactions with the environment, be entangled with our case and can give some leakage of information. It can be very important for quantum key distribution stuff and like this. Going to definition of standard quantum error correction. One thing I would like you to understand is like we need some mathematical description for this, because in classical setup, when we have bits and we want to make a error correction of the bits, we have a little easier scenario, because classically we can take a bit, we can read it, and we can do even something very naive, which to some extent is working. We can repeat this bit many times, and we can encode, for example, 0 as a repetition of zeros, 1 as a repetition of 1. We can copy this information and spread it through multiple copies. So what it will give us, like some code that can be can sustain some errors that will occur on small amount of bits. But in the quantum mechanics, actually do, for example, this randomness of the outputs, cloning quantum state deterministically is not possible. We cannot do this. That means if we have state, and even we know this classical description of it, like making copy from quantum operations, like through operating on that state, is impossible. Although we can, of course, make a copy like by repeating the same experiment, but this is not the same, because through the imperfections, actually, each of the state will be a little different. So no-go theorem, no cloning means we cannot do some easy tricks like in classical quantum error correction. So let's look at the setup of our quantum error correction. We have a state, rho is an input state, and then we have three operations, and S will be encoding in the seminar, E will be the noise, R will be the coding operation, and then what we will expect is like through the useful quantum error correction, at the end, we obtain the same input, the same state as our input state. Here, for example, the noise channel, which will be description of our model of the reality, can be seen as a combination, like some integral over different kind of random noises that can be averaged and can be treated just like a single channel, which will be the given input for our quantum error correction procedure. So what is known and what is the formal definition of quantum error correction? That means like we are dealing with some subspace C of our space Y, which is our vector space. And for this subspace, we have some projector on the subspace. Each state which lies in this projector on the subspace, which is visible in equation under the equation 1, each state can be then corrected, like by the definition, if for the given noise E, we will find deterministic operation such that the composition will give us rho again. So what are the known conditions for this? For example, Kill-Laflamme conditions that give us some algebraic way how to guess the subspace that can be used for given noise, how to guess this then the coding operation. So we have like this kind of operation in equation, sorry, this kind of set of linear equations, sorry, not linear, I mean, depending what we are looking for, but quadratic with the respect to Krauss operators, which are denoted by EI of our channel E. And then this kind of equations, if we can find PC, which is this projector, which is some subspace, and will satisfy for some numbers, complex numbers, these equations, that means for this noise, we can find perfect quantum error correction code. Okay, so let's go a bit further with other analysis, and let's look at some edge examples. So we will just need a definition of what's called Chojnia-Makowski isomorphism of quantum channel, which means like if we have quantum channel and we will extend this operation by identity and use it on this state, which is it's not actually state because it's not normalized, but it can be seen as a maximally entangled state. Then this is then matrix, give us full description of the quantum channel, which is operation. So like we are going one level down, and it's easier to investigate properties of given channel by its Choi-Yamoukowski isomorphism than by investigating it as an operation. So I will explain why we need this. So, for example, let's assume that our noise is some unitary operation U. We know this classical description of this U. It can be some physical process that's making this noise U. So we can find actually infinite many ways how to correct this noise. For example, our encoding can be inverted unitary matrix, and then the coding will be identity operation. This composition of these two channels will give us the identity, so we have perfect correction. We can do something different. For example, keep encoding as identity and decoding as an inverted unitary operation, which will work the same. And the property for unitary channels, which are our noise, the property of its Choi-Yamoukowski isomorphism is that the rank of its Choi operator is equal to 1. On the other hand, we have something which is called maximally depolarizing channel, which, as you can even probably see graphically, if you are not familiar, this is the formal definition by the equation of this channel, is taking our input and then it's tracing it out. There is no connection between input and output. Output is some maximally mixed state that is just some random stuff. So what I mean is like we cannot find any quantum error correction code that will send any useful information from this point to this point. And for that channel, its Choi rank is dimension of y squared. So what are the ranks of Choi matrices? When we have Choi operator, we have channel on some subsystem Y. Let's say the dimension of the subsystem is D, then the rank is between 1 and D square. So what we can think is like, okay, if the rank is 1, we can do many stuff. If it's D square, we cannot do anything. So maybe it's like that. The intensity of the noise can be somehow measured by the number, which is the rank of the Choi matrix, which also is the number of Klaus operators for a given channel. And as I told you before, for unitary channels, we have 1, it's perfectly correctable, and for maximally depolarizing channel, and not only this one, we have D square. Why also this kind of view is important? Because by using Steinspring theorem, each channel can be seen as an extended unitary channel where there is some input state and the additional subsystem is traced out. So actually this noise can be seen as some interaction with the environment. And if this, for example, comes from some if, which wants to get some information about our input state, it can be dangerous because some information from here can get here. But how many information that person can get? It depends on the dimension that we will extend. And actually, it can be shown that the dimension we have to extend our channel, so we have this representation, but the unitary interaction with the environment is equal to the Choi rank of our operator. It should be. Okay, so let's go right now to probabilistic setup. Like first of all, we should think about where will the probability come from, like what is like it about. So we will introduce some operations which are called subchannels. They are like channels, but instead of taking quantum state and providing quantum state, they are doing the output is a probabilistic version of some quantum state. How we can realize this? So we can think that this kind of operation is not something it's only in our minds, only like a mathematical object, but also it can be physically implemented. So if we have input state rho and S as an operation, Then we can find another quantum channel. This is subchannel, this is channel. We can find a quantum channel which will be extended. So we have one output and second output, and we do binary measurement on this one subsystem. This binary measurement will give us two classical labels. And we can, for example, assume that if the label is 0, then we accept the output of this operation. If it's 1, we deny this output, which means, for example, we can ask for repetition, we can ask for another state, or abort the quantum error correction procedure, whatever. The thing is, this kind of post-processing of classical information introduces some probability distribution on our output states. And the behavior of this probability will be the topic of our future slides. So let's define formally what will be probabilistic error correction for quantum channel E. Right now, we can write it as an equation, the same composition of encoding, noise, and decoding. But right now, this composition is not taking an input state raw and going with the output as a quantum state raw, but instead, because it's scaled identity, it will give us some probability that we obtain raw as our output. So exactly by using the same decomposition of or realization of subchannels. And how we can realize this kind of operation. Here we have a channel S and we have a subchannel R. So generally by using like physical processes, we can start with our input state, then use some extended unitary operation. Then this part, which is additional, it can strengthen our correcting procedure will go to trash, we will trace it out. Then this useful information about the raw is going through the quantum channel E, and then we have sub-channel procedure. So here R bar is quantum channel, and we do post-processing of of classical label. If it's 0, we say accept the sigma. There is a chance that sigma is equal to raw. If not, reject it. So we defined the probabilistic version of quantum error correction. So we can think about this probability. Of course, we don't want to repeat experiments too many times. We can, for example, if we find one scheme, we can maybe find another one which gives better probability. So let's say what we want to do is to maximize the probability of success. And this maximal probability of success can be defined for any channel. If it's not correctable, then the success is 0. If it's fully correctable, like perfectly, then the probability is 1. And for as a reminder, for the classical version, the conditions for quantum error correction, there was given by this set of equations where we have S as there was a projector. We can think also as some isometry channel, depending on, isometry matrix, which is seen as a just isometry on that projection that was defined in the Kill-Laflamme picture. And we have this set of equations that if they are satisfied, then we know the probability is equal 1, which means we have deterministic quantum error correction. But we can check if there exists probabilistic error correction by finding right now two matrices, S and R, such that this set of equations holds, or these proportionalities, I should say. Here, EI are these Krauss operators. So here we multiply them like EI multiplied with EJ dagger, which gives us the quadratic number of equations with respect to number of Krauss operators. But here it behaves linearly. So we have less equations, more variables. It should be easier to be done, right? But we have to also make sure the probability is not 0. So we add some additional condition that there is some Krauss operator for which this composition, which is proportional to identity, is not equal to 0. There are many more conditions. I don't want to go through all of them. Just like mention that they have different interpretation and they have different purposes. Like if we treat this equation 7 as our equation for quantum error correction, I just like for simplicity of the notation, I made F as a composition of E and S, so encoding and the channel, then this condition holds even only if we have one of these conditions. So for example, the interpretation like physical of this one, like we have encoding, we have channel, and then we can find a matrix that will rotate our information. And this kind of operation can be seen as a probabilistic isometry channel. Oh, it's not good moment for photovoltaic advertisement. So, what else? Also, we can use this kind of set of equations, which is very similar to Kill-Laflamme condition, such that here we have just additional variable, which is R. And if R is identity, then we are back to our original deterministic version of quantum error correction. Okay, what is the time? Okay, so generally, what we can see is that to answer, like if our probabilistic quantum error correction can be happening, we need to satisfy this these constraints. The number of them is like the number of cross operators, which is a rank of this Choi matrix, instead of quantum error correction, which gives us a square root of this usually. Sorry, square, not square root. Here we have two variables instead of one. And we have some properties, like here is some Hermitianly closed algebra with identity in it. And here we have something which is related to the fact that this is quantum channel. But the thing is, checking if the probabilistic quantum error correction exists, it's easier, as we have here bilinear equations. Here we have quadratic ones. So can we say something about the maximal probability of success? Usually, we don't have too much luck because it was observed even for the deterministic version that finding quantum error correction codes is not a convex problem. We have encoding and decoding. They are totally separate operations. So in the picture of quantum networks, they can be seen as a tensor product of two operations. Tensor product is not a convex. So we don't have luck with using some SDP hierarchy. There is hierarchy for this one, but of course hierarchy is more hard to optimize, but we can of course use it for SDP. But the thing is, optimization, finding such a code for arbitrary noise is hard problem. If the noise, for example, is given by Pauli operators, we use some clever algebraic tricks with groups on Pauli operators, and it works for that case. But if we have general noise that comes from some experimental physical model, then it's harder to find such operations. What else? Maximizing the probability, it's also not easy. And even more, there exists some phenomena that is only related to the probabilistic encoding and not for the deterministic one, that sometimes encoding that uses formal channels that are extended by some additional subsystem, which then is traced out, gives better probability than just pure isometric encodings, which are typically used for quantum error correction schemes. Situation is easier because I told you like this set of equations is bilinear. So what if we will fix just one operation? For example, let's fix encoding. Then actually we can write the SDP program to compute the maximal probability of success, which is given just like a maximization of this linear function. This is the trace of some positive matrix. We have some conic inequalities, and we have some plane that is given by this equation, right? It's not matter about formal definition right now, but the thing is, like we have something linear, we have some matrix, it's positive, we have one conic condition, second conic condition, and some linear condition. In that case, there are methods, SDP, we can use primal and dual problem. We can find with arbitrary accuracy very easily the optimal probability. But the question is like about this probability and the rank of the encoding. I mean, do we have to extend our channel from isometric to general quantum channel? So actually, if we write down this probability as another problem, as a problem of maximization of some mean entropy, where here we're minimizing entropy of output of some quantum channel for sigma, which is quantum state, then we found something interesting because let's keep, for example, to get some intuition visual, let's keep the case for when the sigma is a qubit channel. And let's consider two qubit channels. One of them is like a channel which takes the Bloch ball set of all quantum states on the qubit quantum states and shrink it to towards the center. The second one is doing similar thing, but after compressing it towards the center, it's shifting it somewhere on the right. The thing is like here, the center of the ball, the maximally mixed state is inside. Here is outside this output ball. So if we want to minimize the entropy, which is right now minimizing entropy means that we want to have minimal value of the largest eigenvalue of the given output, means we should focus more on the center, because in the center, for the qubit case, we have maximally mixed state. Eigenvalues are 1/2. The maximal value, the mean entropy will be like logarithm of the 1/2, like with the minus. But the thing is like, we are minimizing the eigenvalue, the maximal one. For the pure states, the maximal one is equal to 1. So what we want to do is to be more towards center. And for example, in that case, we can achieve this when we will take this point on the edge. If we take this point of the edge, we can think which sigma give us this point on the output space. So actually, if we are, this is some topological stuff, if we have output on the sphere of this ball, that means the input was also on the sphere, which means the sigma, the optimal one, is a pure state in that case. But in that case, because here this middle point is inside the ball, then similarly we can show that here the state which goes inside has to be mixed state. Why I'm telling about this? Because the rank of this state implies the rank of the optimal encoding we have to use. So in the case of pure states, we can go with standard notation of quantum error correction, but for the probabilistic version, when there is some point inside, then we have to figure it out some more extended operations, which maybe are more complicated, but give us better probability in the theory. Okay, I don't know how I stand with the time. Maybe I should do some skipping. I wanted to tell some example, but maybe I can skip it. So just say the message of this example. The thing is like here is some formal example that proves that sometimes we have to use mixed encoding, which is kind of not natural for many quantum procedures. The thing is like we have some abstract channel which works on 2 qubits. This channel is like not something we can probably find in the nature, but the thing is just to prove the point and see how it behaves generally, because we want to make some logical statements, but such a example can be treated as a counterexample to our beliefs. And we are going through this example to find the optimal decoding, because due to the nature of this example, we can find the optimal decoding, which is pretty simple. Here we trace out the first subsystem. As you can see, the noise has some of the product structure. So if we want to find our quantum state, like some information about the quantum state, we cannot look on the first subsystem because it's just classical combination of this is just probabilistic combination of classical states. But what about the second subsystem? Here, as we can see, the information about the input is traced out, so no luck for this one. But here, we take input y and we do some rotation and contraction. This is partial trace over first subsystem, which actually can have some information about our initial state, but we are not sure. So definitely the decoding should be tracing out the first subsystem and looking at this measurement result. If it's 0, we should accept and hope for good encoding. If it's 1, we have to deny this. We have to deny this algorithm. So then we are finding by using this conditions from this previous propositions, the optimal input and sorry, the optimal encoding strategy. But this is some geometrical stuff, so maybe I can skip it. I'll do the, we end up with some maximization and we can do the calculation. And what is important here, we can do something like this. At the end, we are ending with inequality that says the maximal probability cannot be bigger than 40%. But if we use less resources, when we use just simple encoding without using extended channel, the maximal probability is 33%. When for operation which has two cross operators, which means we have to extend our channel by additional qubit, the probability grows to 40%. The question is how much this is useful, but this is, I think, subject for different topic. And yeah, summary is like we started with some state, and we through this encoding procedure, partial tracing, noise, and decoding operation, we are ending with the quantum state, which was the input, with the probability of 40% to achieving this one. Okay, so let's go with the last step before we will go to some noise models that can be useful from the picture of NISQ devices. Let's talk about some theoretical advantage of probabilistic quantum error correction. As I told you, the intensity of the noise can be related to the rank of the Choi matrix. So let's define two quantities for the deterministic error correction and probabilistic. We are looking for the maximal value of natural number such that if all the channels have this property, if rank of the Choi matrix is not extended by R, that means the probability, then we can find error correcting scheme and obtain here probability 1 and here probability which is not 0. So we have just two values, and let's think about can we find some bounds or calculate these values to see maybe advantage of using probabilistic quantum error correction instead of error correction. Like we are already reducing the probability of success. Maybe there is some trade-off that we reduce the probability of success, but we gain something, right? So for example, this one, based on some construction known from the literature, we can take these two variables and we can place it here between the fourth root of output space divided by the dimension of the input space. Here we have square root of this dimension y divided by dimension of x, and here we have dimension of y divided by dimension of x. And what we can see by some bounds and some construction of quantum error correction codes, that we have this kind of separation, although it's not like strict. Still, we don't have this. Kind of proof that it cannot be from both sides the middle value, right? So I think what is more important is like here we can see, like if we compare this lower bound with upper bound and put it here, this upper bound with this lower bound, we can see that because we have like intuition, like in this is just intuition, like we have square root of the number of equations to satisfy. That means we can go higher with the number of cross operators, which means our procedure can be more noisy, and still we can find some probabilistic error correction code. Here is some example, like for example, we can calculate for perfectly these values for a small value. And what we can obtain here is like, if we try to encode qubit onto qubit, we don't have any lag. That's, again, for qubit and 2 qubits, deterministically, only unitary operations are reversible. But in the probabilistic way, actually something different happens, because since 2 qubits, we can reverse some quantum process, this quantum noise, which will have Choi rank equal to 2. And such a small procedure gave us some idea for a patent application that we sent to the European Union. And in that patent application, we provided the way how to construct this encoding operations, this decoding operations by using mm, only the machinery that is available in quantum computing setups. So just unitary operations, nothing fancy, just measurements in, let's say, fixed basis and post-processing of classical labels, right? So for example, here we have some classical labels. If both of them will be zero, then there is some positive probability that this even happened. We should accept it because under the condition for this noisy channel, then our output should be this input we implemented. If it's not, then we should reject it, right? Because we don't know if it's the same or not. Okay, and the last one, like some separation, which holds not for all quantum channels, but almost all quantum channels. This is something like, let's say, some mathematical trick not to take all the points, but almost all without some sets of measure zero and blah, blah, blah. The thing is, like in that case, we can separate these two values, R and R1. Of course, they are not right now written R and R1 because we have not all quantum channels. But the thing is, like, if this number of cross operator is not greater than y divided by x, then we can find some error correcting or probabilistic quantum error correction strategy, almost surely. But when we can find the same deterministic quantum strategy, then that means this number of cross operators has to be not greater than dimension of y divided by the dimension of x, and we take square root of it. So we have square root separation between the number of cross operators that can be corrected by using the probabilistic quantum error correction codes. Why it's necessary, why it can be useful for some practical implementations. So first of all, we can fight with errors that are induced by broader class of noises. Because as we showed, we have some separation. Still, our devices are noisy. Maybe we can show that for such a noisy model, we can correct more errors from broader class of noises. The second thing is, because of that, maybe if we want to keep the error model the same level, then maybe the number of resources can drop, which means the number of data qubits can be less. We have seen, for example, to correct noise channel with with the Choi rank 2, we need just 2 data qubits in a probabilistic way. But in deterministic, if I'm not mistaken, it has to be 4. But I can be wrong right now, but it's more than, especially it's more than 2 qubits. Okay. So we should do like 2 adjustments to our model to be more realistic. So first of all, instead of thinking of something precisely, we should think about some approximation that will be enough. If our output state is epsilon close to our input, we should be fine with that. Like if we tolerate that epsilon noise. And what we can expect from such a assumption, right? So for example, if we have the cone and here we have the trace equal 1, which means this here on this line there are quantum states. Let's say we have some pure quantum state that is affected by some noise, and we find the best deterministic quantum strategy, quantum error correction strategy for such a noise model. Then, for example, we can end up in the state ρ1, which is located here. But maybe if we drop the probability of success, we can go closer to that state, which means the probability of success will drop, but maybe there will be some Pareto front, which will have like, for this probability of success, this is the closest state, which will, for example, lead us to this, for probability P, will lead us to this not normalized quantum state, which after observing the success, the label 0, which goes automatically here. So by such a motivation, we can go theoretically closer, but we should prove it. Yeah, we should see it if it's real. Okay, we need we need some measures how to justify some closeness. Let's keep it simple and meaningful. So first of all, for the deterministic strategy, let's take average channel fidelity, where we have composition of encoding, noise, and the decoding denoted by phi. And this quantum channel, we check how close it is to identity channel by checking this inner product with the Choi operator of identity channel. What for the probabilistic way? We will choose conditional average channel fidelity, which checks the same, but under the condition that we successfully recover the initial state. And here it will be given by the trace of the Choi matrix. And the justification will be the average probability of success, which means the average probability that we will, probability that taking as an input maximally mixed state, our procedure will finalize with the success. As I told you, like I wanted to keep it simple and meaningful. So for example, what is simple? We have like linear function with the respect of quantum channel. So optimization should be easier. Also, this average channel fidelity has direct connection with the fidelity, which is like defined for quantum state and is valid measure of closeness, where we have measured the closeness of it's scaled. One Choi operation is actually Choi state. So we have here maximally entangled state to the maximally entangled state, which is given by identity operation, right? And also we can see this implication also without using extensions, just on our input states. So if we average over quantum pure states, this fidelity squared of this input with the output, then this average fidelity is also our like measure from which varies this value of 1 over d plus 1 to 1, right? It's like just operation intuition. The same or similar holds for conditional average channel fidelity. So for this, what we defined here, we have actually, that's why this justifies using this trace. Here, we have maximally entangled state. As the output, we have subchannel. We divide by the probability that it will click, like we will obtain the label 0. And then this quantum state, we look how close it is to this maximally entangled state, which will be if phi is identity channel. And in the same way, this probability of success can be seen as an integral over all quantum states taken with the Haar measure. So this trace of the output, so we can see this is just like average probability of success with respect to inputs that are taken from the Haar measure. Okay, what we can do, the second thing, what we can do about the noise model. So we should maybe make a parameterized family, which will indicate how good our quantum machine, our quantum computer is, which means P will be intensity of the noise in this example. And for example, we can take different parameterizations. For example, sorry. We can take context combination between 1 minus P and P. And here we have identity channel, and here we have our noise with some number of Krauss operators. So if intensity is 0, that means our quantum computer works perfectly. There is no noise. If there is like some positive P, there is some noise, which intensity, like given by this probability, is increasing for the fixed number of Krauss operators. Also, we can find, for example, this model, which is often used in the literature, which is we have independently noisy qubits, such that each of them is under the influence of Pauli channel. So we have with some probability identity, and we have rotation X, rotation Y, and rotation Z on the qubits. So different parameterizations, we can see how the probabilistic setup works for this noise model. So what is our goal? First of all, we would like to achieve high value of conditional average fidelity. This is our like main goal, yeah? But maybe we should add something more, that if there is no noise, which means the computer works perfectly, our weird code will not add up any noises, no any errors. So if the intensity is 0, which means there is no noise in between, encoding and decoding should give something which is not identity, but proportional to identity with some probability. Of course, additionally, we would like to maximize the probability of success. We don't want to keep it low, but the thing is, like, if we maximize like average fidelity and we maximize probability at the same time, like there will be some trade-offs. So let's keep, we just optimize the average fidelity and make some wide guesses what to do with the probability. So let's look at some motivation. Here we have an example of four qubits. Each of them is independently affected by Pauli noise. There is this parameter P, as I told you, rotation X, rotation Y, rotation Z. P is this our probability, is this and intensity. And by using some standard knowledge from quantum error correction, we have a singleton bound that states like if we have we want to encode 1 qubit of information on 4 qubits, and then we know that we will not find a quantum error correction code which the distance will be 3, which means like we can treat it as a distance, as a Hamming distance in classical error correction model, which means if we know there is no 3, then from the classical theory, we know there will be no correction against single bit or qubit errors, right? But there is well-known code which has parameters 412 and can be decoded as a this notation can be decoded as a we are encoding 1 qubit on 4 qubits, and we will get the distance 2. So in that case, we can achieve we can find the code which has distance 2, which means we can find error correction code which can be used probabilistically. What I mean is like, let's say we have some net of bits, like we can think about classical correction. If in our input stays in the input, we accept it. But if it moves, like there is one bit flip, we reject it because we don't know if the bit flip comes from this input state we have or from the another input state that could be implemented, right? So in that case, we reject. So we have some probabilistic code based on deterministic code. And in that case, we can show this conditional average fidelity actually behaves like that. And let's look at this. Here we can see that with this P, which is the intensity of our Pauli noise, we know this average fidelity for the deterministic case will not be higher than 1 minus some linear function. But here is 1 minus square function of P, and this is lower bound, right? So what we know that the error will disappear quadratically fast than this intensity of the noise. So this code is far more superior with respect to average fidelity than this one. But of course, there is a price for it. The price is that our probability of success behaves like 1 over 1 minus 4p. So it disappears linearly. But for example, if we want to have more precise experiment, but we can sacrifice some probability, we can make some more copies, then we will increase the quality of our computation. Okay, I was doing during my PhD some ways how to generate codes for such models. And I will just give a quick recap of what we see here. This is some method. I implemented this and it's available publicly on the GitHub. But the thing is, what is going on here and how hard is to find some probabilistic quantum error correction codes for our noise model, such that we have this kind of condition, which is hard condition, and we want to maximize the average fidelity. So we will do some point 1, 2, and 3 are some preprocessing of Krauss operators. We will take the Krauss operators which are the most important for the definition of our channel. Then for this, we will look for some matrices. Here, these matrices can be found by random guessing very effectively, so we don't have to do any minimization, which is very nice. Then we will define some random subspace for the encoding. And finally, we will define the encoding as the isometry matrix here, such that this encoding is random. So each iteration of this algorithm will produce a random encoding. And if we have fixed encoding, then maybe we can optimize the decoding by using some optimization which is effective for that kind of task. And here we actually this optimization is pretty simple because it turns out this formalis supremum over this average conditional average fidelity can be just calculated by computing computing the infinity norm of this matrix. It doesn't matter how this matrix look, but we have just infinity norm of some matrix which represents our quantum channel, and there is some other products. But the thing is, this is very simple, right? There are so many algorithms that can handle this one. Also, we can do some tricks and, for example, make sure that our probability of success will be higher. So we can introduce to this matrix, we can introduce some decoding, which will be in the same basic as an encoding with the strength over 1 over n. And finally, we can implement a decoding strategy, which is not optimal, but we have some good guesses and some theorems that will show that it is a valid method how to generate some probabilistic approximate codes. So the final thing of my presentation is just to look at some graphs that will show you the results of this algorithm and what we can obtain from this code. Oh, yeah, I forgot. I mean, just like to have in mind the complexity and the properties that can be proved theoretically for our method. So the complexity scales like dimension of the y squared with w. W stands for the multiplication constant. So, for example, for normal one, it's 3, right? But we can use something more effective. It will go to 2. So, like, depending what kind of method, how big matrices we are dealing with. So, it goes like dimension of y to the power of 6, let's say. And what are the properties that we can prove theoretically and what we can observe? Theoretically, we can prove that if the rank is not so big of this choice model, of this choice matrix of our like parameterized family of noises, then for sure this procedure will return an error correcting code that the average fidelity, conditional one, is equal to 1. Also, we observed if we increase the rank of these choice operators, here we increase it by the factor of square, then still we can find the codes that give us 1, but for this one, we have only numerical observation, nothing formally proved. So it seems like the method works. Let's see some examples. Yeah, and of course we can, and this is maybe some comment on the bottom, that we can, of course, make improvement of this algorithm. For example, I told you matrix G was random. We can resample it to choose the best code. If we have fixed encoding or fixed decoding, then we can do alternative optimization between encoding, decoding until it will converge. So we can do such a tricks just to boost a bit our quantum error correction procedure. So for example, here, we have situation, we have y, x, r, k. X is a 2, which means we implement qubit. On y, which means 4, it's 2 qubits. And r is the choice rank of the noise. It's 16, which means it's maximal, it's the worst case. And we are sampling some 10,000 random quantum channels with that properties. And then we can see how behaves many error correcting schemes. So P is the intensity of the noise. Here we have the average fidelity of the success or conditional, depending if we have deterministic or probabilistic setup. So dash line is just like it's some line that can be obtained by getting some random encoding, decoding strategy that has just random and has no sense at all. So in that case, the behavior of that procedure will behave like this. Meanwhile, optimized deterministic strategy goes a little bit higher, with depending on which we will use which method for the finding the coding operation we use. Here is by using path recovery channel. Here is by using SDP. So we have this one, we have this line, we are going up. But what about the probabilistic setup in this one? By using our procedure, this procedure had some hyperparameter, which is fixed here. And by varying this hyperparameter, we obtain these three lines. As you can see, it's nothing impressive in that case, but we could beat deterministic case. For example, for that green line. What about the probability of success in that case? Here, the probability success, depending on the probability of the probability, behaves like that. So, for example, the red one was not so good, and what's more, the probability is not satisfying. But the green and dark one actually gives nice probability, like when, let's say, the intensity of the noise with the time measured in the years on the Earth will go to zero, then the probability will go here to around maybe 88%, something like this. So different example. Here is this case when we have such a fixed parameters that the R is small enough so that actually quantum error correction codes works much better. Here is the reference line. And as you can see, deterministic methods are giving this line. But our method, according to our theorem, which means like we proved it also by using some numerical simulation, that gives us the line which gives us the average fidelity equal to 1. So we can see the difference in the regime of noise, for example, 25%. The difference could be visible, right? Let's see another case. We are just boosting the number of cross operators more with respect to input and output. Here we are encoding 2 qubits onto 7 qubits. And we have error which has 1,000 around cross operators. And we can see, for example, for this very noisy system, the deterministic strategy and the strategy which is stupid one, let's say, reference, then they behave the same. But meanwhile, the average fidelity for our function works pretty well almost in all the range of noise operation, sorry, of the intensity of the P. Meanwhile, for that code, the probability of success also is counting nice. It starts very low, but when the intensity goes to zero, then we are ending up somewhere maybe around 95% or something like this. And for example, here, we choose different parameters, but all of them gave us the same results. These parameters, these hyperparameters. Sometimes these hyperparameters are very important to choose correctly. There is some example. I just choose something like extremal, like 0.999. Then for example, here we obtain probabilistic code, which is even worse than the reference method. Of course, it will have some probability of success, so it's totally disaster. But if we fix it correctly, then we can beat even deterministic codes. So the one example before we are going to Pauli noises, here is also like some example with x equal to 4, which means 2 qubits on 6 qubits right now. And we have r equal to 200. And as you can see, for example, the reference method, which is deterministic codes, behaves like this. The approximate behaves like this. And the probability of success is going nearly to 90%, let's say. Okay. Yeah, and maybe one more example. Just like to show that sometimes we failed with the probability of success for this optimization. Here we choose parameters for which deterministic should work good, like from our intuition. So as you can see, it's pretty good. Of course, then probabilistic returns average fidelity, which is always 1 in all the range of P. But unfortunately, the probability stays, it's not 0, by the way, but it's like 10 to the minus 3, maybe. So actually, it succeeded, but failed at the same time. I showed you before what happens when we have 4 qubits and we have Pauli noises, right? So I tried on that noise model, this code, to see like what kind of results we get. Can we beat the behavior of that induced probabilistic method by the known stabilizer code. So here, as we can see, I just plot this blue line, that is the approximate conditional average fidelity and the probability of success. And they both fit up the line, which is given by this probabilistic method. So maybe this method could be optimal, or we could achieve the same results, which also gives us the boost that the way how we optimize our circuit to find good probabilistic codes can be reasonable. And finally, let's beat some deterministic codes. So we go to we go to symmetric Pauli noise on 5 qubits, and we want to encode 1 qubit of information. So we have a reference method known from the literature. This is known deterministic code for 5 qubits. And of course, it goes, this is the line. Here it behaves like 1 minus square of the intensity. But meanwhile, we could find approximate code such that this red line, probably it also is like 1 minus square root of p, I don't know, but definitely with higher constant, which means here, even let's say our computer is like maybe around 10% noisy, so then we could have almost perfect fidelity in probabilistic way, but we can struggle with some 90% accuracy for the deterministic code in that sense. But there is a cost, for example, here maybe around 50% of the ratio of success. So if we're willing to sacrifice this probability of success, then we can go a bit higher with the experiment. We can have something more precise. And this is last slide from my presentation. Thank you for your attention, and I encourage you to ask me some questions.
I would like to invite you to our next quantum computing seminar, which will be on 19th of June. And we will send the registration link via email. Usually we haven't prepared it yet. So, and I would like to encourage you to come here to see the quantum computer by your own eyes. With this, I would like to thank Richard once more, and have a nice afternoon. Bye.